we are morphing the usual laws of evolution that we know from physics, the laws of quantum mechanics, the Schrödinger equation, any equation. If we morph time into space, we are inventing a new kind of law. It's not a law of evolution. It's not a normal law of physics.
I'm here with Thomas Hertog. Thomas, thanks for joining me.
Hey, good morning or afternoon.
Thomas, let's start off talking about time. The title of your book is On the Origin of Time. And this immediately strikes me as a paradoxical title because the word origin implies a progression from one state to another, a state of non-existence to a state of existence. But one already needs a notion of time for such a concept to even make sense. So in what sense can time have an origin if time itself is needed for that concept to make any sense?
Yeah, so that's an age-old question, right? It goes back, it's a philosophical question for many, many centuries, really. Because as you say, there's a paradox. The origin of time cannot be, well, it can, I suppose, but if you're going to find a scientific explanation for the origin of time, then somehow time itself must morph or change into something else. This was the reason, by the way, that someone like Albert Einstein was very much against this idea of a Big Bang, because to him, the idea of a Big Bang implied a breakdown of science, implied some sort of supernatural act of creation, to get things going. But that reasoning is sort of based on the kind of reasoning that you evoked, namely that, we tend to think there is some sort of external fixed notion of time that maybe even sort of transcends our universe. And then you reach that paradox. Then you can't quite genuinely conceive of an origin of time. But Albert Einstein's own theory, his theory of relativity, leads to a different picture. Because it makes time and space into something really physical, a physical field, something which can change and morph and bend and curve. Not some sort of absolute thing which just exists. Right? So before, people like Newton thought of time as something metaphysical almost, whereas Einstein taught us that space and time are physical things, just like particles and matter. And the most dramatic implication of Einstein's relativity was then the conclusion, reached much later, that time can end and time can have a beginning. In other words, that this physical fabric of space and time, which we can't see, but which makes our reality, which shapes our reality, that it doesn't have a prior existence. There are instances in which that basic fabric of reality can change so dramatically that it ceases to provide a meaningful notion of time and space. An example is a black hole. The big stars at the end of their life collapse. Nothing can withstand the collapse. And in the end, that collapse also destroys inside a black hole space and time. And then Hawking in the 60s famously turned around that argument and showed that these very same methods which had been developed to show that black holes are in a sense the end of time also apply to our universe as a whole and lead to the conclusion that Einstein's theory predict a genuine origin of time. So it is our familiar notion of time itself that breaks down at the Big Bang. So that's still not a solution to the question, of course, what is the origin of time? But it's it shows you how the paradox can be avoided. We shouldn't be thinking. So Einstein's theory didn't give the answer, right? Einstein's theory said, okay, back 13 billion years ago, the fabric, the notion of time ceases to be meaningful. And for in Einstein's theory, this was still some sort of paradox, in the sense that the theory didn't say, well, what happens then? In fact, the actual beginning in Einstein's theory is a singularity, and the theory breaks down. So in a sense, Einstein's theory predicts its own downfall at the Big Bang. But it shows you how to avoid that paradox. It tells us that we shouldn't be thinking of time as a prior thing in which then the universe is created. No, we should try to think of the origin of the universe, of the Big Bang, as the origin of time, as a more fundamental beginning, as a genuine beginning, as something which somehow doesn't have a prior cause. And that has been the challenge ever since the discovery of the Big Bang in the 1930s. That has been the challenge. How can we think? How can we conceive of a kind of physics which does not assume some sort of notion of time as prior input? So it's a grand puzzle. It's a supremely fantastic problem, because this big question that you asked, which was philosophical question for so many years, is now through Einstein's theory. And then there was a Belgian priest, Georges Lemaitre, who explored the consequences of Einstein's theory for the beginning of the universe, for the origin of time, came to the conclusion that it must be something, an origin of such a fundamental kind we haven't thought of. And since then, it's there at the core of physics and at the core of cosmology, this old question. And so that's what my book is about. That's what I worked about with Hawking. It was the question, I think, which was at the center of Hawking's interests for his entire career.
Do you think
how can there be time without time?
Yeah, I mean, do you think we'll ever be able to get to an intuitively or a conceptually satisfactory answer to a question like that? Given the concept of time is so deeply baked into the way humans think about the world. It's in our language. We can't get away from it. Even that sentence, get away from, implies a progression from something to something else. It's so deeply entrenched.
Yeah.
Do you feel we could ever get to an intuitively satisfactory answer to this sort of question?
I would say, well, I feel yes. Yes. Although it's true, of course, we're very, very far away from any kind of intuition. So there are two parts to your question, I'd say. It's true that, and we maybe we talk about it later. It's quite clearly, if you're going to get a grips on the origin of time, and in my book I have a proposal for how we can do this. It is, of course, a very abstract branch of physics. We're trying to develop some sort of new physics, which in one way or another is timeless, which of course is completely at odds with our intuition. But I think that when we develop that physics, and when we talk about it, and when we try to communicate it, and in time, I do believe these concepts will be forged into some sort of new way of understanding, which is accessible to a broad spectrum of people. Our intuition, or which we all share, is not a static thing. Physics has the capacity to slowly change, to slowly let our intuition evolve. So I'm very optimistic in that sense, even though indeed we are dealing with corners of the universe like black holes and the Big Bang, which are of course extreme by all standards.
Yeah, I definitely want to warm up to some of those corners and honestly the truly profound ideas in your book, including the perspective of time as a holographic projection from a lower dimensional space, and the idea that the laws of physics have evolved through some sort of Darwinian process. I think en route to those topics, it's important that we set the scene for your collaboration with Stephen Hawking. Some of the greatest thinkers in history have turned their minds to the topic of time, and I think one of the greatest among them was Stephen, who he was both a close friend and a close collaborator of yours. I sadly never got to speak to Stephen, but I did. My office in Cambridge was one below his, and so I would often cross paths with him. I'd see him, going past the cafeteria, and I always remember whenever he entered a space, the atmosphere would change. There was people would turn heads, and there was this sense of someone with a great presence entering the room, and he was very revered for his intellect. I would love to hear what it was like to collaborate with someone, of that caliber, an intellectual giant of that level.
So you must have met Hawking in the new Center for Mathematical Sciences.
Yeah, so I didn't meet him, but my office was below his in that center.
Yeah. Okay. So I met him in the old department, which at that time was located in the center of Cambridge, just a few yards from the river, really, where his office was adjacent to the common room. So he was right at he was much more than in the new building. He was much more at the center of the action, much more connected also to his colleagues. And he was much more accessible because this was the late 90s. Of course, he was already famous, but the 90s were an era in cosmology with lots of new observations and lots of new ideas. And so when I met Hawking in 97, 98, he was back into research and very excited about these latest observations and theories of the early universe, and that's what interested me as well. And so he took me on as his PhD student, and at that time he communicated with a mouse placed in his hands through computer voice, which worked at the time quite well. And so we would sit in that common room in the old department for hours and hours next to each other, shoulder to shoulder. And he would explain me pretty much, sentence by sentence. And of course, I had an infinite amount of time. And so gradually I think I got to sort of appreciate and share some of his intuition on these ideas in cosmology. So what was happening was that, and so gradually some sort of collaboration formed. First, this was of course much of a mentorship, but then because we got so hooked on these Big Bang questions, our collaboration evolved into any kind of fruitful collaboration you have among scientists. And certainly when I introduced these holographic ideas in cosmology, he was very keen on that. So what can I say? This was just, it happens in a scientific career that you find yourself on the same wavelength with a few people, and somehow over the years it happened between Stephen and me, and it became a very close collaboration, which, when the communication became more difficult, in a sense also almost intimate, because I had to learn to communicate with very few words. And there certainly have been occasions where I thought, okay, Stephen, we can't go on like this. This is impossible. But somehow the human mind finds a way to get through. And it was very intense and very interesting. Precisely because we shared by that time a lot of intuition on the Big Bang, we sort of navigated. And it was, to some extent, also, I think, a lifeline for him, because it's clearly his science which gave meaning to his life, right? So of course he had to adapt in the later stages of his career. I suppose one could say that Stephen was not the usual physicist anymore, because he couldn't write equations. So he had to sort of redevise the language of physics, a little more intuitive, a little more visualizable, a little more daring or outrageous, some people would say. And of course, this had to be combined with calculations and thought experiments, and so we try to sort of collaborate in a way which made it fit into the usual physics paradigm, but at the same time was a way to value Stephen's intuition as well. So yeah, what else can I say? Of course, while all that was going on, he was busy being famous as well. But what I've appreciated is that he kept one foot firmly into research, and he had this second mission, which you could say was about spreading, deepening a broader scientific culture, and through communication and so forth. And the combination of these two, one feeds the other for him. There was always a close interaction between the way he was doing research and the way he was communicating to the broader, to the entire world, really. It's a sort of a striking thing with Hawking, that it's one of these rare physicists who draws his inspiration from almost directly from these big human questions we all ask. These ground questions, like where do we come from? That's ultimately the question in cosmology. And somehow, in ways we don't understand yet, but I'm convinced of this, somehow Stephen believed that we had to get a grip on these deepest questions in order to flourish as in the far, far future. So for him, this was almost this was very much a human adventure. This was sort of it was that serious. It was about our far future. It was about what humanity could ultimately aspire to. And that sort of connection, some sort of cosmic humanism almost, I've always found extremely inspiring and extremely strong in Stephen's life and Stephen's work. So yes, it was certainly a very inspiring figure, and we had a lot of fun. And out of it came, I think, a great new hypothesis on the Big Bang, on the origin of time, which sort of crystallized in our minds a year or two shortly before he died, say. And at some point he told me, look, it's time for a new book. But he could hardly type any word by then. And so that's the reason why I wrote this book.
Yeah, I mean, a good chance for me to plug the book, because it's fantastic. It's a really unique blend of philosophy, physics, and kind of biography of Stephen and your collaboration together. It's a very unique perspective. One of the things that really stands out in reading that book and in being familiar with your work with Stephen is I guess just how bold it is in sort of challenging standard paradigms of the way of conceptualizing time and the origins of the universe. One of the analogs here, which I think is a good analogy to point to, is one of our most basic intuitions of time historically has been that it's sort of fixed in direction and flows at a steady rate. And Einstein, came along and with his theory of relativity challenged the perception of the steady rate. And so, any working physicist today, and I would say most people are familiar with Einstein's work, will now have an appreciation for time not being something that flows at a steady rate. But I think people still very strongly hold the intuition that time has a fixed direction. And I would love to turn to that question of the arrow of time. How confident are we that the arrow of time does indeed have a fixed direction? Could time flow in a reverse direction in any circumstances?
Theoretically, yes, but it's extremely unlikely, right? You break an egg and you rarely see eggs unbreak. But the arrow of time, the clear arrow of time that we have been enjoying for 13 billion years in our universe, through the formation of galaxies, through its expansion, through the formation of higher levels of complexity, complex chemical molecules, planets, life, ultimately. That evolution, which is the arrow of time you're referring to, is perhaps the biggest puzzle associated with the origin of time, because that evolution is only possible if the universe at the Big Bang started out in a very, very, very special way, in what physicists call an extremely low entropy state. And in a sense, we've been taking advantage of this for 13 billion years. If the universe would have started out in some random state, nothing would have happened. And so this is the reason, it's part of the reason why people like Hawking got so interested in the origin of time, in the Big Bang, because it was not just any kind of Big Bang. It was a very special Big Bang. Somehow the Big Bang got it right, in order to give rise, to give birth to a universe which has such a clear arrow of time that billions of years later life could emerge. And so it's the arrow of time. So what's the origin of the arrow of time? That's the really interesting question, or the really interesting facet of the Big Bang. And so it's one of these, you could say it's one of these biophilic features of our universe, and perhaps the deepest one. There are other biophilic features. The observation that the particle forces are just right for there to be carbon. The observation that the dark energy isn't too large so that the expansion doesn't go too rapid, because if the expansion is too rapid, you don't form galaxies. The observation that the Big Bang, the hot early era of the universe, there were slight temperature fluctuations. Well, if these temperature fluctuations had not been there, there would have been no galaxies, and so forth. So there's a long list of strangely biophilic features at the level of physics, at the level of the properties of the laws of physics, which make our universe a habitable place. And the arrow of time that you pointed out is perhaps the most mysterious and the most fundamental feature, because without a clear arrow of time, probably none of these other features would have emerged either. And yeah, so in many ways, my discussions with Stephen were about the question how such an arrow of time can emerge. So if you go further than Einstein's theory, so we talked about the beginning of time in Einstein's theory. It's this singularity. Mathematically, a singularity would mean that the beginning, the actual beginning, is out of science, is beyond science. That was also one of Einstein's complaints, as you can imagine, to Georges Lemaitre, who was a priest and an astronomer. Einstein said, "Look, I mean, you're entering God in the picture here." But if you go beyond Einstein's theory, if you combine Einstein's theory with quantum theory, you can hope to include perhaps not a cause for the origin of the universe, but at least a description of a mechanism how time could emerge from something more fundamental. Because you see, the fabric of space-time is some sort of a given in Einstein's theory, whereas in quantum theory, you could hope that that very fabric, that basic fabric, is itself an emergent property of the world. And you could hope that you could sort of, get a grip on the origin. And so that was where my efforts with Hawking were focused on. We were, for years and years, essentially attempting to apply ideas from quantum theory to the problem of the Big Bang. And in doing so, build a physical theory of that earliest phase of that, what in Einstein's theory was just a meaningless singularity.
Yeah, one of Stephen's famous works, I think not just Stephen, I can't remember who he co-authored this with, but one of his famous papers is the wave function of the universe, and he introduces there, or he talks about there, a sort of a no boundary hypothesis for the early stages of the universe. I guess this touches on your point of bringing quantum physics into the conceptualization of the early stages of the universe. Could you briefly describe the main ideas in that paper and where they've taken us today?
Well, briefly, I don't know, but yes, but it's a famous paper, yes. Yeah. In fact, it was a controversial paper at the time, 1983. Stephen wrote this with Jim Hartle, and Jim once told me that they had trouble getting their paper accepted by the referees because the referee complained that this was so outrageous, that it was just too outrageous of an idea to talk about a wave function of the entire universe. In normal quantum theory, we talk about wave functions of particles. And then Stephen and Jim wanted to talk about a wave function of the entire universe. And then Jim and Stephen asked for a second referee, a second opinion. And the second referee, according to Jim's story, wrote that, yes, the first referee is right. It's an outrageous idea. Yet you should publish this paper because it's going to be important. And so that's what happened. Right. So this was, it's an ingenious idea. But it raised, as often in physics, it raised more questions than answers. But it was very, very stimulating. And in a way, my work with Hawking in the later stages of his career builds on that so-called, as you say, no boundary idea. Okay, maybe I can say two things about it. So Stephen's no boundary theory of the Big Bang. So this brings us back to the 80s. In the 60s, he had shown that Einstein's theory had this singularity at the Big Bang. Classical physics has a singularity. The Big Bang seems to be not part of science. The conclusion was, wait a minute, we're going to have to bring in quantum mechanics. That brings us to the 80s, in which he does so. And that, in fact, no boundary theory was the centerpiece of his book, A Brief History of Time. That was the book in which he first proposed that we can understand the beginning of the universe on the basis of science. And his no boundary idea was a centerpiece of that. Now, what does it entail? Well, we talked about the general idea that if we're gonna have any hope to understand the origin of time, somehow we will have to find some sort of physics in which time emerges from something else. And Stephen's no boundary idea is the first example where a first model where exactly that happened. The way he phrased it was that initially the universe would be pure space in a way. And if it's just space dimensions, as we all know, we can bundle these together and form some sort of sphere, form some sort of no boundary object, like this a higher dimensional version of the surface of an orange. And so he was doing that, and then sort of transforming that purely spherical geometry. He could manage, in fact, to transform this so that it would sort of open up and an expanding universe would emerge. So in a sense, what he did was he was morphing time. When we go back to the Big Bang, he was morphing time into a space dimension, and that gave him the possibility of essentially creating a universe, from nothing, just like a bubble, so to speak. Of course, you can't do this in Einstein's theory. It was hence the word wave function. The bold claim of Jim and Stephen was that a purely spatial geometry would capture some of the profound quantum aspects of space and time, of classical space and time. It was very bold, very, you could wonder why. I mean, what exactly happened? But it was a model. It was a model to sort of escape Einstein's conclusion that the beginning was a singularity about which we can say nothing. No, Stephen and Jim replaced that singularity where everything breaks down with a perfectly smooth, regular sphere, which would be, part of science. So to me, the legacy of the no boundary idea it was the first demonstration that, hey, maybe it is in fact possible to describe the actual origin if we think purely quantum mechanically about the beginning of the universe. The bad news, and now we jump to the 90s, the bad news was that out of this construction, out of this model that these two gentlemen devised, came a universe which was not habitable, a universe which does not have a clean arrow of time. It hardly has any arrow of time. Not much happened in these universes created through this no boundary process, so to speak. And so Stephen realized, by the time I met him, Stephen certainly realized there was a problem with his theory. And this is where his beautiful intuition comes in. There was a problem with the theory, but on the other hand, the construction, the idea of letting go of this fourth time dimension and morphing it into something else was so beautiful to him that he thought there should be some truth in it. So, in other words, he thought there was a kernel of truth in this no boundary idea, but that somehow we were thinking about it in the correct way. And this is really sort of the starting point of my book, of our collaboration. So, in other words, if I relate to what we were discussing earlier, the biophilic universe wasn't in there in his old theory. The universe that he created in A Brief History of Time was empty, lifeless, no arrow of time, no galaxies, no life.
So one quote that you included from Stephen in your book is you quote him saying something that's very profound and quite intriguing. He says, one could take the attitude that quantum gravity and indeed the whole of physics is really defined in imaginary time. And it is simply a consequence of our perception that we interpret the universe in real time. What is the idea of imaginary time, and why is it important in this way of thinking about time?
Okay. Yeah, this is typically Hawkingian sort of oracle talk, right?
Yeah.
Mathematically, the process that I just described about morphing the fourth dimension, morphing time into a fourth spatial dimension, mathematically, this comes down to making time imaginary. So I didn't use the word imaginary time because I think it adds to the confusion in general. But it's basically morphing time into space, and you do so, of course, only in the most extreme examples, corners of the universe where the usual notion of time breaks down. So that's the crux of the statement. Where our usual notion of time runs into a singularity, Hawking sort of made the statement that we can nevertheless do physics if we morph time into a space dimension. But of course, I wanted to say something else on this. Then the second part of the quote, which you read, and this is where it gets interesting. He then says, but wait a minute, maybe the pure space thing is more fundamental. And of course, he says this because we think of the fundamental quantum properties of space-time, gravity, as more fundamental than the classical fabric we have. So somehow he dreamt that maybe in the end all of physics can be formulated in this more fundamental manner, and that we will understand our classical world, our arrow of time, our usual notion of time as emergent properties, as perhaps a little less fundamental. So that's what that quote is about.
Well, I mean, I think it leads very nicely to some of the main ideas in your book. You present there several very profound new ideas, not just about sort of emergent phenomena within the universe, but actually emergence of the laws of physics themselves. And it's earlier we talked about this conundrum that the universe is. It seems very biophilic, we're alive, and there's a deep question as to why. And there are many different approaches to this. One approach that you hear, well, there's several different anthropic type of arguments for this. And one version of that is just, set the universe in motion, and, as long as it's within a certain range of parameters, an evolutionary process will happen, and life will evolve to adapt to a particular environment. That's one way of framing that argument. And I think you've got a much more profound and general way of thinking about this that applies to the laws of physics themselves. Could you walk me through the idea there of this Darwinian evolutionary process of the fundamental laws themselves?
Sure. And in fact, now I remember what I wanted to say earlier, and it provides the bridge towards where you want to go. If we're in this extreme realm of the universe, which we claim can be described by morphing time into space, something very profound is happening. If we do so, of course, any notion of evolution is gone. We only have space. So we are morphing the usual laws of evolution that we know from physics. You go from A to B in one way or another, probabilistic in quantum mechanics or deterministic in classical mechanics, that's all fine. But you go from A to B, these are laws of evolution, the laws of quantum mechanics, the Schrödinger equation, any equation. But if we morph time into space, we are inventing a new kind of law. It's not a law of evolution. It's at best a law of a condition, an initial condition, a final condition, depending on how you look at it, but it's not a normal law of physics. And I think that was what Stephen and all of us were struggling with. What exactly are we doing here? You could call it an extension of physics, because normally the initial conditions and the final conditions are not part of your laws of physics. You specify your initial condition, you specify how you throw a tennis ball, or how you fire off a rocket, or how you set up your lab experiment, and then you do some measurements. That's all not part of the laws of physics that we seek to discover. But of course, the problem of the Big Bang is very different. We were certainly not setting the initial conditions at the Big Bang. And we certainly can't repeat the experiment. And so somehow we have to find a way for physics, for the laws of physics, to tell us what was happening. We have to include those initial conditions, those ultimate initial conditions, at the Big Bang, not as external things to specify, and this is sort of part of the problem with God and all that, right? But as part of physics. But if we want to do so, we have to invent a new kind of physics, a new kind of law, a law of a type which physics has never really been confronted with, because normally you can always find some sort of boundary conditions external to the system you're interested in, to specify those, except with the Big Bang. And so this is tied to this biophilic character of the universe. It's tied to the mere fact that we exist. We are not we're not looking at the universe from the outside. So the Big Bang, and certainly when it comes to the biophilic nature of the Big Bang, why we exist, what is this mysterious connection between the universe, its evolution, and the fact that life emerged, that's now the kind of question where it is clearly wrong to put yourself outside the universe and try to create it as if we're looking down on it from some sort of godlike perspective. So it's the kind of question, and this was really behind so many conversations that I had with Stephen, like, look, we have to sort of almost turn cosmology inside out, almost look at the whole problem, look at the whole of physics differently, try to sort of put ourselves in the equations in one way or another, in order to avoid this. In order to avoid the paradox you run into when you try to describe the universe as if you're outside. And so the anthropic principle that you mentioned was sort of the first grain of that kind of thinking. but it was very artificial, because the anthropic principle is, well, if you could call it a law, I would not call it a law, but I don't know how I would call it. Some sort of dream or so. I don't know, some sort of, all right, let's call it a principle. The anthropic principle is something you add afterwards. You have your usual physical theory. I think if people using the anthropic principle in cosmology probably have in mind some sort of multiverse theory, some sort of physical theory, a normal law which happens in a big space and produces many universes, bubbles, and the theory is normal physical theory. So you look at that multiverse, you look at that ensemble of universes from the outside. Then, of course, you realize you have a problem, because the theory itself doesn't tell you in which one of these universes we should be, and therefore what we should observe. Do you say, but there is something like the anthropic principle, which is not a mathematical thing. It's not part of your theory. It's some sort of additional thing which you add in order to select, this is our universe among this zoo of universes. And you could credit the anthropic principle by saying, at least it puts the spotlight on the problem. There is this mysterious, we are here, our universe is habitable. We got to find a way that doesn't come out of physical theory just like this. We got to find a way to reconnect, if you wish, the laws of physics with the fact that we are here. But it's a reconnection which happened in a very artificial way, because there was no connection between the theory and the equations and the anthropic principle. And also, so it didn't quite work. If your zoo of universes has a few that are habitable, the anthropic principle will not tell you which one is better. So it still will not predict which one we should be, or its predictions will depend on your preference, my preference. You might have your notion of what's anthropic, I might have a different notion. We would end up in a different universe. The theory, to phrase it in the old Popper kind of terms, the theory isn't falsifiable. And I think Stephen was one of the first to realize how profound that aspect, that the non-falsifiability of the multiverse, how profound a problem that was. At the time, late 90s, early 2000, many cosmologists, because it has a certain appeal, right, to some people. And it's very popular now in a way, right, in popular culture. I think scientists, many of our colleagues, I think thought we're gonna fix this problem. We're gonna somehow find some sort of way to make it all work. But I think Stephen early on thought, hey, it's signaling that this idea of a multiverse may not be the correct way of thinking about the problem, that there's something more profound going on at the origin. Because you see, a multiverse, a big space with many bubble universes, is in some ways kind of conservative. It's sort of saying there is a global notion, an eternal notion of time. There is a big space out there, and it's just being constantly filled with universes. So it sort of tries to avoid thinking about the origin of time at the Big Bang as a truly genuine origin. It sort of tries to say, well, maybe it's not a really fundamental origin. It's just one Big Bang out of many Big Bangs. And So we developed a different way of thinking about this whole thing, much more inspired by quantum theory. The big asset that quantum theory brings, quantum theory brings two different elements to this game. One famously is that quantum theory allows us to bring in us in the equations, bring in the observer as part of the theory. So an observation in quantum theory is not something which happens in abstractio from the outside, independently of the system. No, the act of observation is part of the theory, is part of shapes, influences, determines, impacts how reality manifests itself. The questions we're asking become intrinsically interwoven with the kind of reality that is revealed. So, and of course, in daily life, the universe is what it is, and it is very classical. But if we go to these extreme corners of the universe, inside an old black hole at the Big Bang, that profound feature of quantum theory becomes important. There is no a priori given reality. No, it becomes contingent on the sort of questions we ask. And then the second thing that quantum theory emphasizes is, of course, the role of accidents, the randomness, the probabilities, the fact that we need not live, we need not find ourselves in the most probable universe, because along the way, lots of accidents could have happened. So we're familiar with this idea, of course, from biological evolution. What we do, or what we did, was to sort of extend that notion of randomness and selection effects in the early universe all the way down to the level of physics. What was happening in the earliest stages of the universe was a series of transitions through which gradually the forces and the particles and the composition of the universe took shape. And we've always thought there should be some sort of grand explanation of this, like some sort of fundamental theory. But if you think this process through, all the way back, where even time itself gets incorporated as one of these transitions, you reach much more of a Darwinian view on this early process, a view in which you look at that branching process of physical forces much more as a Darwinian process in which the laws of physics we have today, the particles, the forces, the composition of the universes, the dark forces, and so forth, are the result of an evolutionary process which played out in the very earliest phases of the universe. And if you take this back and you arrive at the trunk of that sort of tree of laws, so to speak, according to our hypothesis, what you find is not a fundamental theory, but is the disappearance of the notion of a physical law itself. That no boundary construction sort of popped up again in our final hypothesis, but now not as a sort of a creation event, but more sort of going back in time as a disappearance event, as a disappearance of the notion of a physical law. So it was a shocking conclusion, because remember, we were to get a grips on the origin of time. So On the Origin of Time, the title of my book, is of course a variation of Darwin's title On the Origin of Species, because we're trying to ultimately deepen that kind of Darwinian thinking about evolution, including the laws of physics. But what I was saying was that, so it was sort of a shocking conclusion that this law of initial condition that we were trying to find, the law of a Big Bang, the law of a beginning, was in fact also turned out to be also the origin of law. And so the Big Bang in this thinking becomes almost, no, not almost, I think, frankly, it does become what I would call an epistemic horizon. Quantum theory seems to so it's something very special about quantum theory. It's a theory of what we can know, what we can measure and all that, but it's also a theory of what we can't know. In normal quantum theory, we cannot know the position and the velocity of a particle. When we now applied these quantum ideas to the Big Bang, it's almost like that quantum theory is telling us, is protecting us from wanting to know too much. It takes the laws of physics themselves and transforms these, morphs these, let these smoothly disappear. It's very special.
I'm very interested in the ontological claim being made and the ontological thinking behind this process versus, I guess, how, I don't know if there's a traditional way of thinking about the quantum multiverse, but I think when many people think about the quantum multiverse, they imagine sort of a continuous branching of things that could happen. The probabilities and things interact and things get entangled. We get entangled with, let's say, a particle that could be spin up or spin down. And then in some sense, both of those two branches exist. There is a mat entangled with spin up and mat entangled with spin down. And both of them within their own sort of like a quantum branch perceive the universe as, either one with a spin up particle, one with a spin down particle. And then there is some sort of sense that ontologically both of those branches exist in some sense, but the observers within them can only see their own branch. I'm interested to understand how you think about in the sort of conception of the emergence of the laws of physics as we see them. What is the ontological status of this branching? Is the idea that sort of every possible arrangement of the laws of physics in some sense exists, but by our being here, we are only privy to sort of a certain very small, very narrow subset of them? Or is it, am I misunderstanding that?
Yeah. So what you describe is normal quantum theory, or how you would apply quantum theory to the wave function of entangled particles, or to the prediction of future outcomes of future experiments. But so in cosmology, we're trying to do the reverse. We're trying to predict the past from the present, so to speak. Yeah? So, but you could ask the question: okay, suppose you conceive of all possible laws of physics. I think that this is your question, right? Suppose are they all out there? That's your question. They're one giant wave function encompassing all possibilities. My answer would be there is not. My answer would be that so this wave function, yeah, it would not be calculable. My answer is that this is asking too much, because that wave function, that hypothetical wave function, encompassing all possible laws of physics, someone could then come along and say, hey, that's the final theory, right? That's the theory which sort of transcends our universe. The crux, the ontological crux of our hypothesis is that this is not where physics is gonna lead us. The crux is that in a cosmological context where we are within this universe, that the laws of physics are fundamentally contingent on that observational perspective, and that we are confronted because of this mere fact that we exist and that we look up and around with an ontological limit when we come to the Big Bang. And in fact, and that's the reason for this last, so there's a certain finitude, if you wish, a certain finitude associated with what you could call our basic human condition. And in that sense, I think it's, and maybe this is also where you're getting at, a little bit of an ontological readjustment of what physics and cosmology ultimately tell us about the world. It's true that for centuries, more and more, in fact, the idea that we are searching for some sort of objective truth, which in a way, stands above the universe, transcends the universe, was born in the scientific revolution 5 centuries ago, and certainly since Newton has been sort of the in the back of the mind of physics and science. This has been sort of the paradigm. You're right. I mean, the ontological crux of our hypothesis is that physics, deep down, is much more like how we think about biology since Darwin. And so that provides a different beacon, a different angle, a different perspective on where we're going.
It's really hard for the mind to pass, because I think many people think about even a Darwinian process as something that exists within physics. They think of an evolutionary process exists within physics. It's some sort of higher level version of that.
Right. So that's the comforting part, of course, of the Darwinian story, because in the Darwinian story in biology, you could always calm yourself. How do you say this? There's always a level below chemistry or physics or whatever, and so it's comforting. I think that's what you were saying, right? Whereas if we're now going to apply this Darwinian process to physics itself, there is no level below. And so this indeed has been in the back of our mind. Laws of biology, laws of human history, they're all emergent laws. But down at the bottom, we have these fundamental, fixed, not changeable laws of physics. And so as a foundation for anything else, I'm saying there is no foundation. I'm saying that even those laws are rules that are emergent, contingent on our observational situation, and they're not unchangeable, rock solid rules guiding the creation of the universe. Yes, that's the crux of our statement, and in fact, that's the reason for this somewhat more adventurous chapter in my book, and on holography. Holography is our new way of bringing together quantum theory and relativity. That's a whole story on its own. But let me just briefly say that in this new way of making relativity and quantum theory work together, in fact, it's exactly like that how it works out. It's Darwinian. If you apply holographic ideas to cosmology, it is the time dimension, the past. It's the time dimension which is the one which holographically pops out, which is the emergent dimension. So it's the one dimension what was the problem from the beginning with Big Bang cosmology. And from a holographic perspective, if you go back in time, you lose more and more information encoded in your hologram. And the Big Bang is nothing but the limit. You run out of bits, you run out of information. It's so fundamental that the theory sort of evaporates. And I was very surprised, and Stephen too, that whole no boundary thinking, and that idea that this time dimension doesn't, in a sense, morph into space, or holography goes further. Holography says the time dimension just disappears. And with that, of course, any notion of law, any notion of causality just disappears as well. So I was very surprised that these ideas of holography are beautiful, they're brilliant, but they have been discovered in purely mathematical context, in string theory, in a sort of a mathematical laboratory that has nothing to do with our universe. And then somehow, when we start to apply those ideas to an expanding universe like ours, they seem to do exactly what this top-down intuition, this Darwinian intuition that we developed does. So in a sense, it was what the doctor ordered for us.
Yeah, it's I think once you've really looked deeply into just how well all those mathematical pieces do fit together, it's almost impossible not to be drawn into the belief that there is something very profound happening here. But your book does end very sadly with a sort of a presentation of all these new ideas, and then, you know, as you said, look into the future. No resolution as of yet as to where these go, whether it would turn out to be true about how the universe works. I would love to know, as we sort of come towards a close, you know, what is next? What is the next steps to understanding whether this is indeed the way the universe works?
Right. Yeah, you say, yeah. So as you say, this is a new hypothesis. It's out there now. It builds on. I mean, the book is there now, but the hypothesis, of course, within our community of scientists was in the making for many years. So it's really much more, I mean, I've tried to write a book a little bit as a detective story, right? Because we too did not know where we would end up with this. And that's the cool thing about this kind of research. It's very, it's like a discovery story. But as you say, this is theoretical physics. And ultimately, how can we now test this thing? How can we now, where do we go from here? I do believe that we have resolved the paradox of the multiverse. And so remember, the multiverse was not even testable in principle. It was not falsifiable because the predictions of the theory itself were ambiguous. You were claiming we're living in this universe, and I was claiming we live in that universe. And so you can't test it if these two universes differ in one or another property. There is no rational way of setting this. Now, by building in this observational perspective from within the universe, by turning cosmology inside out, we have resolved this fundamental falsifiability problem. But that doesn't mean, of course, in practice that we can test it, because this sort of Darwinian process that I evoked early on in the universe, these laws of physics, they sort of crystallized a fraction into the expansion, and they've remained the same ever since, as far as we know. And so they act, for all practical purposes, as a foundation for everything else. But how can we probe this evolutionary character all the way in the beginning? It's very hard, because these earliest phases, light cannot even penetrate in those earliest stages, because the universe is a huge, there is no light really. It's too dense. So you can hope maybe with the new observations of gravitational waves. Gravitational waves, they penetrate anything, right? They go right through everything. So if that earliest phase in which the laws of physics as we know them are forged, if that goes together with the generation of bursts of gravitational waves, well, those gravitational waves can't disappear. They will weaken, they will spread, they will stretch, but they should still be out there. and maybe future detectors, future observations of gravitational waves can dig deep into the sort of, it's almost like a bus underneath layers and layers of other gravitational waves. So that could be a possibility for a more direct hint of that earliest phase. And so our hypothesis predicts very strongly that earliest phase goes together with a burst of inflation, a burst of very rapid expansion that generates gravitational waves, and those might be detectable, and that would be a strong hint, I think, that we're on the right track. But you can think of a completely different, well, that's the first point, maybe gravitational waves from this early phase. The second point is obvious. The second prediction is less precise, but very much obvious. I think our hypothesis predicts that we are going to find many more properties of our universe that seem miraculously accidental, that seem just like when biologists reconstructed the tree of life. There are all these random accidents. And you see, since the 90s, we found a few, but we haven't, the tree of laws of physics, we barely know this tree. We barely have any, I mean, to express it in Darwinian terms, we barely have any fossils of this earliest phase yet. So I think if we're going to find more fossils, if we're going to find dark matter particles, dark matter forces, all sorts of things, the accidental nature is only going to be stronger and stronger, and not weaker and weaker. I think that's a clear prediction of our hypothesis. And maybe we find some sort of slight traces of that early evolution. You could imagine that, okay, the laws of physics have crystallized early on, but maybe one or another feature of the laws kept slightly evolving. People are looking for that. People are looking for whether the constants of nature, for instance, whether they were the same in the earliest phases of the universe, or whether they slightly change. That would be a strong hint that also the laws of physics, have an evolutionary nature. So that's the second sort of line by which you can hope to test these ideas. And the third is completely futuristic. The third and final thing that I wanted to say on that is that it has everything to do with that idea of holography. These holograms that theoretical physicists are talking about, these holograms are essentially strongly coupled systems of quantum particles. They are not so fundamentally different from the kind of quantum systems that engineers are developing to try to build a quantum computer. And so there is this completely weird and fascinating connection slowly taking shape in physics, in science, in engineering, that maybe nature is some sort of quantum computer. And maybe by studying quantum computing, we can build systems that have certain properties of these holograms that cosmologists are dreaming up to describe the early universe. And maybe, I don't know, this is maybe 10, 20, 30, 40 years in the future, maybe there's some sort of completely new way of doing cosmology on the horizon, in which we do cosmology in the lab by constructing quantum systems that have certain properties of these gravitational holograms, with emergent gravity and emergent time and all that. And I don't know where this can take us, but it's truly fascinating that there is a link on the horizon between quantum engineering, quantum information on the one hand, and these age-old problems of the Big Bang on the other hand. Where this will take us, I don't know, but that's certainly stuff for another book.
Yeah, well, I wait with bated breath for that other book because, for just to mention again, this your book was excellent. Stephen's first book, A Brief History of Time, was excellent. I read that when I was still in high school, and I look forward to in my later years reading the next Thomas Hertog book. I think this is a good place to bring it towards a close. One of the things I love to ask my guests towards the end actually pertains to the topic of books, which is, most of them are incredibly well-read people, and they've been inspired by books and they've gifted books. And I would love to hear from you. What book have you most gifted to other people, and why?
Yeah, that has changed. That has changed a lot over the years. But lately, I've spoken with a lot of people from different walks of life about this book by Hannah Arendt, the philosopher Hannah Arendt, The Human Condition, which was written late 50s, early 60s. And it also relates very strongly to the movie Oppenheimer, to the situation with the atomic bomb and all that. So somehow, it's a wonderful link between her thinking and the questions that I elaborate on in my book, which I had not discovered before Stephen died. And so this is something that has touched me and that I've spoken about with many people. And of course, it would have been great to discuss her ideas, notably on the finitude of science and even physics inherent in our human condition, and her searching for answers and not finding it in the science of her days. It is a sort of curious link between Hawking's later thinking and her ideas, which I think deserves to be explored. And the book also, is timely in so many ways today, not only with the Oppenheimer movie, but also with questions to do with artificial intelligence and how we should deal. How should we deal with this problem that new science and the technology flowing from it has always this risk of escaping us? It is, she was worried about it, and now we are 40, 50 years on, and we should be even more worried about it. So that's been on my mind lately, that book.
Yeah, fantastic. I'll link that one into the notes as well.
Oh, cool.
Last question. We've talked a lot about time. We've talked a lot about collaborating with smart people, and we've said that a lot of the world's most intelligent people have been drawn to these fundamental questions, whether it's in fundamental physics or, as you just said, artificial intelligence. And I would love to get your thoughts. If we were to one day be visited by an artificial superintelligence, something vastly smarter than we are, and we had to pick somebody, either past or present, from human history to represent us to this superintelligent other, who would you pick?
Well, maybe we can send Hannah Arendt and Stephen Hawking together.
That's a fantastic answer. Fantastic. I think that's a great place to wrap it. Thomas, thank you so much for joining me. It's been a pleasure.
Pleasure. Thank you.
Hello, audience. Thanks for joining me for today's conversation. If you're finding this podcast valuable, please subscribe to the channel and check out some of my other videos. Please also feel free to comment with guest suggestions or other ideas. It's all very much welcome. Thank you for joining me, and I hope to see you again next time.